Every software application exerts a specific mathematical demand on hardware. Often, these demands require mutually exclusive optimizations to run with any degree of efficiency. Take an operating system. It must register a keystroke, allocate memory, and manage network traffic in rapid succession. The logic is unpredictable and branching. To handle this, the hardware must minimize the delay between resolving one instruction and starting the next. This is a low-latency problem. This diagram illustrates the conflict. On the left, our operating system navigates a complex sequential path. On the right, we see a high-throughput problem. Rendering 3D graphics or training a neural network requires performing the exact same mathematical operation on millions of data points at the same time. A single processor cannot be perfectly optimized for both single-thread latency and massive parallel throughput simultaneously. Forcing these conflicting workloads through the same architecture creates a structural bottleneck. The Central Processing Unit, or CPU, is the engineering solution for general-purpose computing. Its design prioritizes low-latency control and the flexibility to jump between highly varied instructions. The Graphics Processing Unit, or GPU, is the solution for data parallelism. It is built to repeat the same operation across massive datasets, prioritizing total volume, or throughput, over the speed of any individual task. Form follows function. The CPU is a versatile controller. The GPU is a parallel accelerator. The capabilities of these processors are dictated by the physical layout of their silicon dies. This CPU die contains a small number of execution cores, typically 4 to 8. These units are large, sophisticated, and powerful. However, they occupy only a portion of the chip. Large blocks of silicon are dedicated to intricate control logic and local memory caches. This control logic is essential for managing complex sequential paths. It allows the CPU to perform branch prediction and reorder instructions to keep irregular software tasks moving efficiently. The GPU architecture uses that same silicon real estate to achieve a different objective. By stripping away the complex control logic used by the CPU, engineers fit thousands of smaller, simpler processing cores onto the same footprint. This trade-off is effective because massive parallel workloads avoid complex branching logic. They only require executing repetitive mathematical operations in perfect unison. Physical allocation determines capability. Investing silicon in control logic yields versatility. Investing it in core count yields throughput. Thousands of cores are only useful if the memory system can keep them fed with data. This diagram shows the CPU's reliance on large local caches. These allow the processor to rapidly fetch and swap small, constantly changing data required by an OS. In contrast, the GPU minimizes local cache, prioritizing high bandwidth access to external memory. High bandwidth is critical. The GPU must move large, predictable streams of bulk data, like image pixels, into its cores without causing a bottleneck. These structural differences also redefine our understanding of power efficiency. Efficiency depends on the workload, not just the hardware. A CPU is more power efficient when handling small, sequential tasks. Activating a massive parallel array to process a single logical thread would result in significant energy waste. On large datasets, the GPU becomes the more efficient choice per unit of work. By spreading calculations across thousands of cores, it completes the task in a fraction of the time. However, there is a caveat. Because a GPU activates thousands of cores at once under heavy load, it will draw substantial total system power. Optimal efficiency is only reached when the hardware's delivery method matches the software's structural requirements. Modern systems do not choose between these processors. They employ a cooperative pipeline known as heterogeneous execution. The CPU orchestrates overall execution, handling main program logic, like game physics. During a data parallel stage, the CPU sends data across the bus. The GPU takes over, processing the workload simultaneously across its thousands of cores, then returns the final results. Peak performance in this model requires minimizing transfer delays across the data bus and carefully timing the handoff between processors. A system's true capability comes from the seamless offloading of specific computational burdens to their optimal processor. By understanding these architectures, we can categorize real-world software tasks with precision. Recalculating a spreadsheet formula or processing web browser logic are CPU-bound tasks. They rely on quick decision-making and sequential control. The GPU is reserved for high-volume operations. Applying a filter to millions of pixels or multiplying massive matrices for machine learning requires massive parallel throughput. This also addresses the core count myth. More cores do not improve performance unless the software is specifically written to execute instructions in parallel. This is why the GPU cannot replace the CPU. A system always needs a processor to handle the complex control flow and coordination. Mastering computer architecture requires looking past raw metrics like clock speed. It requires an understanding of how specialized hardware solves distinct mathematical problems.